Okay, so welcome back. This video we're going to be going over principal stresses. We're going to do an example problem with this. So this is the same stress element that we looked at in the last problem. So we have the same sigma x, sigma y, and the same shear stress. So just as a review, right, our normal stress in the x direction is negative because it's going into the body here. Our normal stress in the y direction is positive because it's coming out. And then our shear stress, our tau xy, is negative because if we look at the right side of the element, we have a shear stress going down. So that's going to be a negative. So our goal here is to determine the principal stresses. So if you remember from the overview video we did, the principal stresses are where I have we're trying to find where we have a maximum, where normal stresses are maximum. And these are the principal stresses. So we also know that our shear stress, if we have maximum normal stresses, our shear stress is going to be 0 in this case. So I kind of wrote out the procedure here of how we're going to do this. Our first step is to find the angle, find the orientation of the element when we have our principal stresses occurring. So remember, if we rotate this some angle, right? So if we rotate this whole element some angle, right? And let's say we start out at x and maybe we go here, right? It's going to be some angle that we're trying to find when we rotate this where our normal stresses are going to be maximum. So let's do that. So we're going to be using the equation over here. So tangent of 2 times the angle where we have principal stresses is going to be equal to tau xy over sigma x minus sigma y divided by 2. So we know that in this case, we're going to be doing the tangent of 2 times theta p is going to be, well, our shear stress is negative 30, and then it's going to be divided by negative 75 minus 40, and that whole thing is going to be divided by 2. So we're going to end up getting that 2 times theta p is going to be equal to 27.55. So that means that theta p, in this case, is going to be equal to 13.776 degrees. And this we can call theta p1 because there's going to be 2 solutions to this. So since maybe you remember from the other video, is that 2 theta p1 and 2 times theta p2, how many degrees away are these going to be? These are going to be 180 degrees apart, right? Which means that theta p1 and theta p2, these are going to be 90 degrees apart. So we can do either way. We can either add or subtract 180 to this number, the top number here, or we could add or subtract 90 from this bottom number here. So let's just do the bottom number. It's a little bit easier. So if we add 90 degrees here, we're going to get a number greater than 90 degrees. So we usually want to keep it either plus or minus, in between plus or minus 90. So I'm just going to go ahead and subtract here. So if we do that, we're going to get that our theta p2, that's going to be equal to negative 76.22, call it 4. So that's going to be negative 76.22 4 degrees. That's going to be a theta p2. So now we have this done, right? We found the orientation of the element. So now we need to find the principal stresses. So to do that, we're going to be using this equation here. So let's do that in a different color. Let's do that in orange, right? So now we're going to want to find what our principal stresses are. So we're going to write this equation equal to Sigma x plus sigma y. Well, sigma x is going to be negative 75 plus sigma y is plus 40 divided by 2 plus or minus the square root. It's a big square root. Sigma x minus sigma y. So that's going to be negative 75 minus 40 divided by 2. That whole value is going to be squared, right? Plus negative 30 squared. So if we look up here, our tau xy is negative 30. Yep, negative 30 squared. So negative 30 squared is going to be the same thing as 30 squared. So we'll get a plus minus here. So you're going to end up with sigma 1. Sigma 1 is always going to be the bigger one, right? So sigma 1, if we do this out, is going to be 47.356 megapascals. Sigma 2 is always going to be the smaller one, or the one that's closer to the negative value. So that's going to be negative 82.356 megapascals. So these, in orange here, are our principal stresses. So if we rotate this 13.776 degrees, we're going to have these principal stresses here. These are going to be our two maximum normal stresses, and we're going to have a shear stress of 0. So we can imagine if we draw our element, right? So maybe we have a coordinate system. This is our original coordinate system, x and y. And now we have this element. And now maybe it looks something like this. We're going to have, we don't know what direction these are yet, right? Maybe it's something like this, right? And this is going to be, if we expanded this out, this is going to be 13.776 degrees. And since this 13.776 was positive, that means I'm rotating counterclockwise. So this is the way it's going to be. But we don't know if this one is going to be, so I shouldn't have really drawn these arrows here. We don't know which one, if the x is going to be 82.356 or the y is going to be 82.356. So what we need to do is check. So what we need to do is check one of them. So if you remember from the last video, we have our normal stress transformation, our general transformation equation. So a normal stress transformation equation, this is it, right? So we're going to plug in, this will find us our transformed x value, right? So we know whatever answer we get here is going to be what the value is for this x value here. So let's do that. Sigma x, so we're going to be using our original ones here. So this is sigma x plus sigma y, right? So that's just going to be negative 75 plus 40 divided by 2 plus negative 75 minus 40 divided by 2 times the cosine of 2 theta p. Now we could write 2 times theta p1, or we know that 2 theta p here is 27.55. Right, plus tau xy, which is negative 30, and then sine of 2 theta p, which is going to be 27.55. And since we use this angle, this positive angle, we're going to get this guy here, this one, that's the 13.776 away. If we do this, we're going to get our transformed x value is going to be equal to negative 82.356 megapascals, which is the same thing up here, right? So we know that this works. We have the right values here. And that's negative, so we assumed our arrow the right way. So this value here is going to be the negative 82.356 megapascals. Then if this one is the negative 82.356, then this one up here, the top one, has to be the 47.356 megapascals. Right? And what's our shear stress going to be here? Well, think about that. What's our shear stress going to be? Well, our shear stress, since this is where the principal stresses are, our shear stress of the principal stress is always going to be 0. So we don't have any principal stresses, any shear stress here. So we can conclude, right, that this is what our transformed diagram is going to look like, our stress element, and where we have our principal stresses. So that's using the equations way. Next video, we'll probably do, maybe look at Moore's circle, which is a graphical way of doing this. All right, thanks.